I want to introduce Heiko Schoenfuss. He's going to talk about mixtures of contaminants of emerging concern that are common in Great Lakes tributaries and the effects that he's found.
Thank you, Steve. Good afternoon, everyone. I will try to spend the last talk of this session to take some of the field data and bring them back into the laboratory and trying to establish some connections there. Acknowledgements, there's a lot of people involved, just like the last speakers already mentioned, and of course, a lot of funding that came from the Great Lakes Restoration Initiative, our collaborators in the Fish and Wildlife Service and some of the other agencies, and the disclaimer as well. Now, it's worth stopping ever so often and think about this ecosystem that we're studying. The Great Lakes hold about 20% of the global surface liquid water supply. That's a pretty amazing amount of water. And of course, it's a system that holds this for a very long period of time, so we do have to worry about long-term effects. The ecological significance of that system is matched by its economic significance, and I think the tension between those two has been something that has been with us for the last 200 years, being the birthplace of modern manufacturing, and coincidentally, or maybe not coincidentally, also the birthplace for many environmental toxicological methods out of necessity to deal with these legacy contaminants that we have been trying to clean up for the last 50 years or so. In the process of cleaning those up, we recognize that there are other contaminants, these contaminants of emerging concern we have been discussing, that may have their own effect and may impede some of the restoration of the Great Lakes. And so, of course, that's what brought us together here. I don't think I have to mention to this group what contaminants of emerging concern are, but it is worth remembering that they're largely biologically active compounds. They're biologically active by design, whether they're pesticides or whether they're pharmaceuticals, and they're tremendously diverse from a chemical perspective, and that's something very hard to deal with when it comes to assessing biological effect. Dan, in his previous talk, already mentioned the tremendously rich data set that was gathered by the Fish and Wildlife Service and USGS between 2010 and 2014, roughly 500 water and sediment samples analyzed by over 200 analytes, CCS, using common methodologies, the National Water Quality Lab of the USGS. So we have a really rich data set that we draw from for all of the studies that I'm referring to in the rest of my talk. Some of that was just published by Elliott et al. In PLS 1 just a couple of months ago. There's a second manuscript on the mixtures as well. And not surprisingly, the basic message is CCs are ubiquitous in the Great Lakes tributaries. You see here several spikes, some of them Dan Gefal mentioned as well. The Chicago area certainly has some very high concentrations of CCs, and other urban centers around the Great Lakes as well. As an aquatic toxicologist and biologist, of course, we were interested in correlating biological effects to this ubiquitous presence of CCs. And we studied 6 riverine systems between 2013 and 2014 around the Great Lakes. You see them listed on this map. 2 of those rivers, the Raquette River in upstate New York and the Cuyahoga River, we were able to sample in both 2013 and 14. We used a very broad array of tools to get a very large and very rich data set that justified the large data set that we had on the chemical side. We collected, or we attempted to collect, 40 sunfish at each of these field sites. We were not always successful, and we looked at a whole range of different endpoints. Knowing, if you do field work, how difficult it is to get a nice matching set of fish in the environment at so many different sites, we hedged our bets a little bit. We also caged fish and took the same endpoints. So we're analyzed in exactly the same way. The caged fish came from a rearing facility, so a known exposure history, a much closer matched set of fish than we would have had with the resident fish. Altogether, we analyzed about 2,500 sunfish. 2/3 of them were caged sunfish, the rest of them were resident sunfish. And I just want to point out again, if you plan on doing field studies, even under the best circumstances, there were a lot of sites where, for one reason or another, you just don't get fish. So the caging of fish is really a nice way to get around that. So now we have 2 really data-rich matrices, a chemical matrix of literally 80,000 data points and a biological matrix that added about 30,000 more data points. And that's the point where you get this t-shirt. What do we do with all the data? We can run ANOVAs till we turn blue, and that's not going to help us. So we spend a good bit of time collaborating with the USGS and coming up with analysis tools that would probably give us something more integrated. And ultimately, we decided on a canonical redundancy analysis that can handle two equally rich data matrices and provide us with some inference about the grouping of sites by chemistry, the grouping of biological effects, and then the correlations between biological effects. You can read this very similarly to a PCA plot. Your first axis gives you the greatest explanatory power, in this case about 48%. The second added another 18%. So that's actually a pretty good explanatory power for an analysis of that size. If we first look at how the sites were grouping together, you see in the red box sites that were particularly contaminated with the CECs through our analyses. And if you were in the previous talk, these are actually sites that match very nicely with what Dan Gefell identified as being sites that are likely to have adverse effects on biological organisms. The sites on the right, especially down here, include a couple of locations that were actually relatively clear of chemicals, so they fall out at the other end of the spectrum. That gave us some assurance that we were on the right path, that we're seeing the separation between contaminated and clean sites. Up here, again, the Cuyahoga River and multiple sites in the Chicago area. This is a wastewater-dominated system. It's almost 100% wastewater, so it's not surprising that we have high CC concentrations. The Raquette River in upstate New York, in the Adirondack Mountains, beautiful sites, most of them relatively clean. If we look at the biological effects, we are also seeing some really interesting correlations, and of course that's what they are, correlations. We see that glucose is one of our main stressors, stress drivers. Long arrows indicate stronger responses, and glucose groups nicely with our liver values. Of course, it is the liver where the glucose is stored. And then we have in a reverse or inverse correlation with our body condition factor and the maturity of these organisms. So what we're seeing here is something that is a classic stress response. We have an organism that's being exposed to contaminants that infers a stress on the organism. Glucose concentrations in the bloodstream go up to deal with this energetic stress. As a response, the liver changes histologically. We see histological as well as organ level changes. And ultimately, that may have an effect on the reproductive output of the fish. I say may because in a field study, it is very hard to actually assign a reproductive effect to those kind of responses. So the next step was, can we go back in the laboratory and maybe try to recreate some of these effects and see whether or not we are getting a reproductive signal, some effect on the reproductive ability of these fish. We were looking, again, collaborating with the USGS, on patterns in the occurrence of CECs in this very rich CEC data matrix. This is a cluster plot. On the top, you have the Great Lakes tributaries clustering out. On the right side, you have our commonly detected CECs. We used a 30% detection as our cutoff to make this doable. And indeed, we're finding that there are some sites, mostly urban sites, that have a certain signature, and other, mostly agricultural sites, that have a somewhat different signature. We use that as a starting point for our laboratory investigations, again, using the data-rich matrix that we had from the 2010 through 2014 studies, and we came up with two mixtures. I'll show you those in more detail in a minute. Each of the mixture at multiple concentrations was then used to expose 3 successive generations of fatted minnows. We started out with adults, breeding adults of the F1 generation. Let me use the pointer here. We followed their reproductive output. We reared the larvae, the F2, what I refer to as F2 generation, continuously exposing them, and then again following their reproductive output all the way into the F3 generation. If you keep track, that's about a year's worth of work, and of course that's why we have graduate students. Thank you. All right, I can say that. Here's our urban mixture. I don't want to go into details. I can't even find the button. But again, you can see here several different pharmaceuticals, DEET, the insecticide, and then we have other compounds that are generally associated with anthropogenic activity in urban settings. And I'll get right to the meat of this 3-generation study, the F2 fecundity. What we're seeing here is actually Three different trajectories. We have a low and medium concentration that are significantly higher than our control fecundity outputs right here. And then we have a therapeutic hazard, if you want. And then we have, oops, what happened? A high concentration of our urban mixture that actually depresses our reproductive output. So that is consistent with our field studies demonstrating that there are changes potentially driven by energetics that result in lower output of these fish. Obviously, the increased reproductive output is probably more interesting from a biological perspective. The use of antibiotics in our mixture may explain that. There's a couple of other compounds that may actually make it easier for these fish in a laboratory setting to do well. Our agricultural mixture, there's some overlap because some of these compounds are so ubiquitous, you will find them in just about every mixture. DEET is one of those if you live in the upper Midwest. Obviously, there's a couple of herbicides in there as well. And again, looking at the same fecundity graph, second generation, we're seeing exactly the same pattern. Our low and medium concentrations are higher than our control, and then our higher concentration falls out below the control. It is a little harder for me to explain why we had increased reproductive output in the low and medium concentration since the antibiotics were not in this particular mixture. We're still working on that. Putting that together, essentially we're dealing with an environment in which CCs are ubiquitous, but their presence is somewhat predictable in patterns. We have mixtures that are found in urban environments and include a lot of pharmaceuticals, a lot of other urban manufacturing compounds, and we have mixtures that reflect more agricultural land use in the surrounding area that include herbicides, pesticides, and so on. We do notice that our resident fish experience an energetic stress. That was the part where we used our field data to analyze those fish. And that energetic stress may result in declined fertility or fecundity. But again, it's a correlative study in the field, so you really can make that conclusion. But when we go into the laboratory and we are recreating similar conditions, we do see indeed another alteration of reproductive output, which strongly suggests that there is some causal relationship between the presence of these mixtures and the observed environmental effects. Having these compensatory therapeutic effects or therapeutic hazards, if you want to call those, makes it, of course, a lot more difficult to model those effects, but that is something that's being done in the near future. This was obviously a very quick overview. There are two talks on Wednesday. In the second part of the session, I want to point out, Lena Wong will talk about the urban mixture in more detail, and Nicholas Cipoletti will talk about the agricultural mixture. Thank you.
We do have time for a couple of questions.
Yes, the question was, fatted minnows are not necessarily representative of the species diversity in Great Lakes tributaries. And that's an excellent point, and one that we sometimes forget when we're in the laboratory. Fatheads are just too easy to work with. We're doing some work with bluegill sunfish, addressing some of that, and then we're using some molecular tools to hopefully extrapolate to other species that may not lend themselves to the same degree to laboratory experimentation. But I believe the issue of species sensitivity is really one that needs to be addressed, because it's not the fathead minnow that we have to worry too much about. It's some of the other species. Thank you. Yes?
Michael, that's a really interesting set of experiments you did. But I'm wondering, when you look at the cumulative fecundity, can you actually say those medium, low, control, and high are statistically different?
Yeah, we did analyze them statistically. It's a little bit of an artifact of the length of those graphs. We have about a 20% difference in reproductive output.
But is it statistically different if you look at your replicants?
I believe it is. And I know what you're getting to. There's a number of different ways to analyze those data. And we actually had that discussion the other day. And I do want to use a couple of other approaches. This was a repeat measures ANOVA, but there are other ways to analyze it, which would probably strengthen that further. Yes. All right. Up. Thanks for that question. I didn't address the actual exposure concentrations we used. Our medium concentration was the highest measured concentration we had in this large data matrix. So that was the highest one. Now, saying that, we measured at times of the year where we wouldn't expect to find really high concentration. It was neither first flush nor really low flow conditions. The lower concentration was 1/10 of that, which is definitely in a realm where you would expect in a lot of these riverine systems to find those concentrations. The high concentration was 10-fold that, so we have a 100-fold difference between our lowest and highest concentration. Lowest and medium are actually environmentally measured concentration. The highest one is more of a worst-case scenario. And it was interesting that if you want to use the term low, it was actually our environmental medium concentration. All right, I think it's blinking. That means it will explode. Thank you. Let me just say the next one.